Hello. So we'll see how this talk goes because I don't know how the rabbit hole for like particle physics goes pretty deep. Yeah, fantastic. I saw the quantum generalized models. I was like, if it weren't right before, I would have been in there watching along. Yeah. So the first part of this presentation is going to be a very brief introduction to the standard model. Just showing you guys the particles, and then depending on how much time we have left, because that's freaking awesome, by the way, we can actually get into actual data analysis. Like what cuts did you make on the data in order to calculate the mass of like the Z boson? Hopefully we have more questions. I'm gonna try to leave a lot of question time because that way I'll know what's actually valuable to you guys as opposed to, hey, here's all the information I've ever collected about this stuff. Okay? Fantastic. Thank you guys all for being here, by the way. Okay. So how many people have seen this before? Yeah, you have a lot of energy. That's good, that's good. Okay, so most of matter is made up of these particles and electrons. Here you have your force mediators, and here's the Higgs boson. I don't have time today to describe why we need the Higgs boson, the Higgs fields, but after this talk, we can talk about that too. You don't have to memorize any of this stuff. I will say the muon is the only particle that you probably didn't use in like a chemistry class or something like that will be discussed today. Up and down quarks make up protons and neutrons, and you guys know about electrons. Okay? Okay, let's see if this works. Yeah, videos are awesome. Visualizations really help. Okay, I should also probably talk a couple things. In order to find these very, very small particles, we smash like 10 to the 10th protons going like 99% speed of light. And you can see particles that haven't existed since like the beginning of the universe. How many people here have heard of the LHC, Large Hadron Collider? Nice, nice. When I'm amongst nerds, I feel like I'm amongst friends. How many people here know what a hadron is? Fair enough, fair enough. So hadrons were made of that quark material, but I have you here, so I'm like, did I talk about mesons? No, not today. So there's a couple different experiments that are going on surrounding the LHC, and the one that I actually did data analysis with was from Atlas. So this explains Atlas better than I could.
In a 27-kilometer underground ring near Geneva, protons are accelerated to near the speed of light and collided. Here at the CERN laboratory, scientists can recreate the conditions of the universe immediately after the Big Bang. The huge Atlas detector, which studies these collisions, took several years to assemble, but through animation, we can watch it in a few minutes. Throughout much of the Atlas detector, there is an intense magnetic field. This is produced by passing current through about 80 kilometers of superconducting cables housed within a large toroidal structure. This enables ATLAS to maintain one of the world's largest volumes of intense magnetic field. It is important to measure the energies of particles which pass through the detector. This is done by a device known as a calorimeter. ATLAS has several types, which are arranged as barrels placed in both the center and at the ends of the detector. The 3,000-ton tile calorimeter is composed of steel and a special material which lights up when particles pass through. The tile calorimeter surrounds a second calorimeter, which consists of lead bathed in liquid argon, which is cooled to minus 180 degrees Celsius. This is known as the electromagnetic calorimeter. Outside of the calorimeter, there is a further component which measures the trajectory of charged particles called muons that reach the outermost layers. The surface area of this component, the muon detector, is around the size of several football fields. Close to the heart of the detector, several components are designed to measure the trajectories of passing charged particles with an accuracy of close to 1/100th of a millimeter. One component, known as the transition radiation tracker, consists of several 100,000 tubes filled with gas and gold wires. Inside the transition radiation tracker are several detectors built out of silicon and divided into millions of thin strips and tiny pixels. The ATLAS detector is designed to measure as many particles as possible, and further detector modules are placed at the ends to measure particles produced at small angles to the proton beams. Toroidal magnets are placed at both ends of the detector to produce the intense magnetic fields that ATLAS needs. The detector construction is finished with the addition of further layers of detectors for measuring particles which reach the edges of ATLAS. Now let's look inside the detector. Here we can see in more detail the pieces of individual components. The tile calorimeter. The electromagnetic calorimeter. The transition radiation tracker, and the silicon devices. In reality, a scientist would not be allowed to walk through the open detector, but in this case, it illustrates the sheer scale of the ATLAS detector. Now we can finally witness the ATLAS detector measuring the particles from the colliding protons. A typical collision produces many hundreds of particles, and each component of the ATLAS detector is necessary to build a full picture of the collision. If you want to know how it all works, don't miss Episode 2, The Particles Strike Back.
That was a pretty good model of it. This is what it looks like in real life when it's of course, not in use. So this thing generates a ridiculous amount of information every year, on like the petabyte level. The next short video you'll see basically describes how they collect the data and how they kind of ship that around the world. Most of the stuff that I interacted with was not experimental data, it was the Monte Carlo stuff. So you can check like, hey, this is what my theory says we should get. What did the experiment say? When the Large Hadron Collider was broken down for a number of years, it took a lot of like PhDs who were writing papers like extra years longer because it was broken. That kind of sucks. All right. guys tell that like a physicist didn't make this video? That was obviously made by someone who like does that for a living. It's impressive. All right, so when you're looking for a particle that you don't know if it exists, you kind of make a theory about it. Back, I want to say 1964, Higgs and like 4 or 5 other guys put forward their papers. And it took 48 years before it could actually get tested and confirmed that the particle existed. That's a good run for funding stuff. So, what particles can we see? We can see electrons. Well, I say see, like we can detect electrons, protons, and muons. And so what is a muon? A muon is like an electron, but it's roughly 200 times heavier. It doesn't live very long, but if you get them to go faster, because of special relativity, it thinks that it's living the same amount of time. So you can get it to go a distance that's longer than you can predict without special relativity. That's kind of cool. When a Z boson decays, 2 of its decay modes are into muon and antimuon pairs. And so if you see one particle going off in this direction, and you see another particle going off in exactly the opposite direction, when this starts happening like thousands of times, eventually you can't ignore it. There must be something there. One analogy that was used is like if there were an alien race that came to Earth and they couldn't see patterns of black and white. If they saw a soccer match, at first they'd be like, what are they doing? And they might think that people are just running around in the field. But eventually they might conclude that there's some ball, some particle that they just simply cannot see, but still exists. That's how things like the Z boson and all the other particles of the standard model that we can't see directly, that's how we know they're there, because we've done this like millions of times. Now, why do we care about the Z boson? We care about the Z boson because the Higgs boson is predicted to decay into a pair of Z bosons. So if we can see enough pairs of Z bosons, well then some particle is there. Perhaps it's the Higgs, perhaps it's not. Now we're pretty confident it is the Higgs particle. But you have to run it through a bunch of other tests before you say, okay, this is the Higgs boson that was predicted by those theories. So you generate Monte Carlo data, or in my case, you get it from CERN, from one of those tier 2 centers. And at first, like you have a ton. This is after some of my selection cuts. A lot of them have like no energy or like null events, and so usually this peak looks like down here, and then you have like a big bucket that's like over here. You cut those out because it doesn't make your graph look pretty, and then you want higher energy. Your data looks better when you go for higher energy particles. In order to say how you calculate the invariant mass, or what is the invariant mass, I would have to write out. So you guys know like E equals mc squared? You've heard that? Well, it's not the complete story. It's actually E squared equals the mc squared, that quantity squared, plus the quantity PC squared. When you subtract that momentum side, like so if you have E squared, you subtract that P squared side, and you take the square root of that to find the invariant mass. And you say, hey, does my distribution match what the physical theory tells us? And if your theory doesn't match the experiment, usually you got to go with the experiment. So anyway, there's 5 minutes left, so I'd rather take questions because I don't know what you guys know and what you don't know, and that's very stressful for me because then I don't know what's valuable and what's not. So let's just go to that.
Questions?
If you didn't clap, you're right. I'm kidding.
Thank you so much. That was really interesting. I guess this is more along the line of kind of the selection of what you're looking at. What sorts of algorithms are you using when you simulate the standard model pieces that you want? Are you like doing a Bayesian method of within a tolerance, or just kind of simulating things and then using machine learning to kind of sift through everything?
Yeah, I'll be honest. How the Monte Carlo data itself is generated, I don't know much about. That kind of gets passed to me. And then we were using a lot of scientific like data analysis framework called Root, which has a strange name because like root means other things too. But anyway, we use Root and C++ a lot. Recently though, Python's of course blown up. So a lot more of the analysis is happening with that. But Root is that package, and we can talk more about that. I can share links that way. Did I accurately answer your question, or did I answer your question to some extent? The answer is I don't know. Yeah, fair.
Any more questions?
Sorry.
I'll get you next.
You'd mentioned that you cut out some of the data to make.
Yeah.
What
yes.
percentage of the total data set was cut out?
Gosh, most of it. Well, so in case you guys are actually going to be like, this guy doesn't know shit, excuse my language, I appended an old talk to the back of this. So let's see. This is what the data looks like without cuts. Yeah. Well, so it says uncut, but it's not fully uncut because some data is cut at like a physical level, like back at CERN, and I don't believe the data that would have been generated, they wouldn't pass to us anything. If there's only 1 in 10,000 of those original like events that come through, they wouldn't. I'm saying this. I don't know how to say this correctly, so I'm going to stop that. But if you see, this is that first bucket where most of the events, or many of the events, are events we don't care about. I just don't know whether many of these are done at that physical level when they choose 1 out of 10,000, or at the like software level where it's 1 event out of every 100. Does that make sense? So this bucket, that's the first thing you cut out. Let's see here. Now these are the different cuts you make on your data. This is momentum. So, oh, there you go. I guess at the end, by the way, you have 74%. I guess, yeah, I forgot. So yeah, you have about 74% from this particular run. But I don't know if that's just this particular case or if that's the average. Does that make sense?
So is that 74% data thrown away or kept?
Kept. Yeah.
We got one over here.
Hi, thanks so much. You were mentioning something about working with Markov models in the intro of your talk. The Markov models, if you could speak a little bit about that.
Sure. I didn't really work with like Markov processes or anything like that. It was Monte Carlo generated data. Sorry. Not really. Not really. It's not. I wish I could. But yeah, yeah.
More questions?
Yeah.
Thank you. back on that graph where you had cut out a bunch of the data.
Sorry.
Yeah, no problem. So yeah, this one, and you had the zoomed in one where you could see the peak more clearly. You don't need to go to that. But.
Okay.
So I might have missed this. You might have explained it, and I might have missed it. But what did you interpret from this, like the spike around this this peak at 91? So
of course, this is not a continuous distribution. There are small buckets.
right.
And many of the events fell in this 0, or I don't know if they classify non-events as -1. I don't know if they have like a special categorization, but
I guess I'm trying to ask, like, did this prove something that you were setting out to prove? And I missed what it was like showing you.
yeah.
Like
So
meaningfully.
when you're trying to match the experimental data with what your theory says, you want to have your software ready for what does our theory say? What does that like kind of curve look like from the theoretical perspective? Because if you need to generate like this line, and then you have data that like overlaps it. If I end up getting an experimental curve that is like over here,
right, and it doesn't.
well then
line up.
this line's wrong. And a lot of the work at the time, so this is back in maybe 2010. A lot of the work at that time was more on the theory side and not on the experimental side, because it wasn't fully up and running until years later.
Okay.
Yeah, I interpret it as very low energy events.
Okay. Thanks.
One final question. Going once? Going twice? All right, we're good. Thanks.
Thank you guys.